Welcome to Inorganic Chemistry. Have you ever wondered why salt crystals form perfect little cubes while other minerals form entirely different shapes? Today we are going to explore the radius ratio rule, a simple but powerful geometric concept that helps us predict exactly how atoms pack together in three-dimensional space. Let us dive in. To understand how atoms form solid materials, imagine you are trying to pack large basketballs into a giant shipping box. No matter how tightly you arrange them, there will always be empty spaces or gaps left between the balls. Now, suppose you want to fit smaller tennis balls into those leftover gaps. The size of the tennis ball is crucial. If it is too small, it rattles around loosely. But if it is too big, it will force the basketballs apart and ruin your neat, tight packing arrangement. This exact same concept applies to atoms. Now that we understand the packing analogy, let us apply it to chemistry. In an ionic crystal, the large basketballs are usually the negatively charged ions, or anions. The smaller tennis balls are the positively charged cations. The radius ratio rule is a mathematical guideline that predicts how these ions will arrange themselves. Specifically, it helps us determine the coordination number, which is the exact number of nearest neighbor atoms that are physically touching a central atom. By comparing their sizes, we can predict the geometric shape they will form. This brings us to the mathematical formula used to calculate this ratio. The formula is beautifully simple. We find the radius ratio, represented by the Greek letter rho, by dividing the radius of the cation by the radius of the anion. Because we are dividing a length by a length, the units cancel out, leaving us with a pure decimal number. As the size of the cation increases, the ratio increases, which physically means the central gap is larger and can accommodate more anions around it without them bumping into each other. Now that we have our formula, what do the numbers mean? Chemists have created a standard reference table based on geometric derivations. If your calculated ratio falls between 0.155 and 0.225, the atoms form a flat trigonal planar shape with three neighbors. Between 0.225 and 0.414, they form a tetrahedral shape with four neighbors. From 0.414 to 0.732, it is an octahedral shape with 6 neighbors, and up to 1, it forms a cubic shape with 8 neighbors. Before we move on, let us see this with a concrete example. Suppose we have a crystal of sodium chloride. We are given that the radius of the sodium cation is 95 picometers and the radius of the chloride anion is 181 picometers. We need to find the coordination number and predict the geometric shape. Our approach is straightforward. We will use the radius ratio formula we just learned. We substitute 95 for the cation radius and 181 for the anion radius. Continuing with our calculation, we divide 95 by 181, which gives us a ratio of 0.524. Now, we look at our standard ranges. This number falls perfectly between 0.414 and 0.732. Therefore, we can confidently predict that sodium chloride has an octahedral geometry. Physically, this means each sodium ion is surrounded by exactly 6 chloride ions, which matches real-world experimental observations perfectly. Let us try a slightly more difficult applied problem. Imagine an oxide anion has a radius of 140 picometers. What is the absolute largest cation that can fit into a tetrahedral void without forcing the oxide ions apart? To solve this, we must remember the boundaries for a tetrahedral void. The perfect fit is the lower limit of 0.225. We set our ratio to this exact boundary and substitute the given anion radius of 140 picometers into the denominator. To find the unknown cation radius, we simply multiply both sides of the equation by 140. We are scaling the ideal ratio up to the actual physical size of the anion. The result is 31.5 picometers. This means a cation of exactly this size will fit perfectly into the tetrahedral gap. If the cation were even 1 picometer larger, it would begin to push the oxide anions apart, distorting the perfect packing of the crystal. Now that we have used this formula and its table, let us understand where those specific boundary numbers come from. We will derive the exact mathematical boundary for an octahedral arrangement, which is the point where the radius ratio equals 0.414. An octahedral void is a gap created when 6 large anions surround a central space. To find the perfect fit, we only need to look at a flat, two-dimensional cross-section through the middle, where 4 anions form a square with the cation in the center. Here is the visual representation of that flat cross-section. You are looking at 4 large circles representing the anions, arranged in a perfect square and touching each other. Right in the middle is the smaller cation, touching all 4 anions without pushing them apart. Notice the right-angled triangle drawn between the centers of the atoms? The side of the square is simply 2 anion radii. The diagonal line passes straight through the center, covering 1 anion radius, the full diameter of the cation, and another anion radius. We will use this geometry for our proof. Let us translate that diagram into mathematics. First, the length of the edge of the square formed by the anion centers is simply 2 anion radii, so the side equals 2r minus. Next, the diagonal consists of 2 anion radii plus the full diameter of the central cation, giving us 2r minus plus 2r plus. Now we apply the Pythagoras theorem to the right-angled triangle formed by 2 sides of the square and its diagonal. We set the sum of the squares of the 2 shorter sides equal to the square of the diagonal. Continuing with our derivation, we simplify the left side. Squaring 2r minus gives 4r minus squared, and adding 2 of them gives 8r minus squared. On the right side, we factor out the 2 before squaring to get 4. Next, we divide both sides of the equation by 4 to make it simpler, leaving us with 2r minus squared equals r minus plus r plus all squared. To remove the squares and find a linear relationship, we take the square root of both sides. Now for the final steps. The square root of 2 is a known mathematical constant, approximately equal to 1.414. We substitute this value into our equation. Next, we subtract 1r minus from both sides, which isolates the cation radius on the right side, leaving 0.414r minus. Finally, we divide both sides by the anion radius. This proves that for a cation to perfectly fit an octahedral void, the radius ratio must be exactly 0.414. So, we have proven that this geometric boundary holds. This brings us to an important reality check, the limitations of the radius ratio rule. While it is an excellent starting point, it assumes atoms are perfect, hard, incompressible spheres like billiard balls. In reality, atoms are made of squishy, flexible electron clouds that deform. Furthermore, it assumes bonds are completely ionic. In the real world, many ionic bonds share electrons slightly, which forces atoms into specific directional shapes that ignore simple sphere geometry. Therefore, treat this rule as a helpful guideline, not an unbreakable law. Let us summarize what we have learned today. The radius ratio rule provides a beautiful, simple geometric way to understand the microscopic architecture of crystals. By simply dividing the size of the positive cation by the negative anion, we can predict their coordination number and how they will pack together in 3-dimensional space. We even proved mathematically where the octahedral boundary of 0.414 comes from. Even with its limitations regarding squishy atoms and covalent bonds, it remains one of the most powerful intuitive tools in inorganic chemistry. Great job following along.